Imagine stepping outside in what should be a mild spring and feeling the air bite like deep winter. A week later, the same sky presses down with a humid heat that feels more like a late summer in a different country. Rivers that slept quietly for decades suddenly rip through towns in record floods, while forests that used to stay damp enough to resist fire now burn so fiercely the smoke crosses oceans. News headlines talk about a once-in-a-century storm every few years. It feels like the rules of weather are being rewritten in real time. So what is this really? Random chaos, or a pattern we have not yet learned to read? To find out, we are going to follow one of the strangest rhythms on Earth and watch how it reaches right into your life. If you zoom out from your own day, your life is already built on cycles. You wake and sleep, eat, work, rest. Your heart beats, your lungs rise and fall. The planet beneath you is no different. It spins through day and night, leans toward and away from the sun through the seasons, drifts through slow rhythms in its orbit and tilt. Some of these cycles are so steady we barely notice them until they break. Others are so long that no single human lifetime can feel their full rise and fall. Yet altogether they create the narrow band of conditions in which your daily weather exists. Scientists often divide these patterns by their tempo. There are very fast changes, the individual storms and sunny days that we simply call weather. There are middle-length swings that play out over a few years or a few decades, which we experience as hotter spells, unusual droughts, or a string of snowy winters that seems to defy the trend. Then there are the slow giants that take tens of thousands or hundreds of thousands of years, reshaping coastlines, melting and rebuilding ice sheets, reorganizing the entire climate system. Those slow giants once seemed like distant curiosities, interesting for books and documentaries, but safely beyond your personal horizon. Yet buried among these patterns is one climate cycle that refuses to stay in the background. It may already have changed the price of your food, the smoke in your sky, the strength of your allergy season, even the path of storms that rolled past your hometown. It is not a hypothetical pattern that only shows up in ancient rocks. It is a pulse in the Pacific Ocean that switches every few years, and when it does, the whole planet flinches. You have heard its name, even if you have never had reason to think about it for more than a headline or two. We call it the El Niño Southern Oscillation. El Niño on its own refers to the warm phase of this pattern, when a vast patch of surface water in the tropical Pacific becomes several degrees warmer than usual. La Niña is the cooler phase, when that same stretch of ocean runs unusually cold. Southern oscillation is the swing in atmospheric pressure that dances along with those temperature shifts. Put together, they form a seesaw that tips the normal balance of winds, clouds and rain over half the planet. That might sound a little abstract right now, but hold on to the image of a huge oceanic seesaw. In a few minutes we are going to lean on it and see what falls off. To understand why this one pattern matters so much, it helps to look at what happens when it goes to an extreme. In the late 1990s, the tropical Pacific slipped into one of the strongest El Niño events ever recorded. On satellite maps of sea surface temperature, the usual cool streak of water along the western coast of South America faded away. In its place grew a bright tongue of heat that stretched out along the equator like a glowing scar. For people on land, this was not just an interesting pattern on a screen. Peru, a country where coastal deserts are normally dry and dusty, suddenly endured staggering rainfall. Some regions received around 16 times their typical annual total, turning streets into rivers and hillsides into mud. Far away in Indonesia and parts of Australia, the opposite happened. Rains that usually nourish rainforests and farmland failed to arrive on schedule. Forests dried out to the point where sparks became infernos. These fires sent plumes of smoke hundreds of kilometers downwind and released huge amounts of stored carbon back into the air. For farmers waiting for reliable monsoon rains, the delays were more than an inconvenience. They meant failed crops and rising food prices. If you have ever seen a news image of distant flames tearing through a landscape and wondered how that could possibly be connected to water temperatures on the far side of the world, You were watching the distant hand of El Niño. The oceans themselves paid a price. Coral reefs thrive in a narrow comfort zone of temperature and water chemistry. During strong El Niño events, that comfort zone can vanish. Warmer than normal surface water can linger over reefs for months, pushing corals past their limits. In the event from the 1990s, scientists estimate that roughly 16% of the coral reefs on Earth died. Many more were pushed into a mass bleaching event, a kind of slow-motion crisis in which corals lose the symbiotic algae that feed them and glow ghostly white. Some reefs have started to recover, but others have never fully returned to their former complexity. If you have ever dreamed of diving on a vibrant reef and found yourself staring instead at pale, damaged skeletons, you have met one of the quieter faces of this cycle. What makes this so unsettling is how global the reach is. The El Niño southern oscillation does not simply flip one region from wet to dry and call it a day. It changes the odds of different kinds of weather in many places at once. During El Niño years, winters in parts of Canada can become milder and drier. The southern United States, especially around the Gulf Coast, often turns wetter than usual. In the Western Pacific, from Indonesia to Australia, fire season can flare up as soils and forests dry out. In some parts of the world, farmers see familiar but amplified patterns and try to adapt. In others, the impacts arrive as surprises, because the local weather does not feel like it should be tied to some faraway patch of ocean. It might be tempting to write this off as an obscure curiosity, something that matters mainly to meteorologists and climate scientists. Yet if you live near a coast, rely on agriculture, pay attention to insurance rates, or simply like to breathe clean air, this pattern is already living rent-free in your future. Climate models and historical observations both tell us that strong El Niño and La Niña events shape not only the year they happen, but also the years that follow. Droughts can start or end under their influence. Fisheries can boom or collapse. Disease-carrying insects can shift their ranges as temperatures and rainfall patterns change. Even if you never learn another technical term, understanding that your weather sometimes answers to a distant ocean cycle can change how you interpret the forecasts that scroll across your phone. The story of how we discovered this cycle is surprisingly human. Centuries before satellites and computer models, fishermen working along the coast of Peru and Ecuador noticed something odd in certain years. Around the time of Christmas, the usually cool and nutrient-rich water that supported their livelihoods would turn unusually warm. Fish catches would plummet. Equipment and techniques that had worked for generations suddenly failed. They began to recognize these warm, unproductive years as a repeating pattern. Because the shift often appeared near the celebration of the birth of Christ, they nicknamed the event El Niño, the Christ child. What started as a local label for disappointing fishing seasons would later become the name for one of the most powerful climate rhythms on Earth. As global trade expanded and communication between continents improved, more people started to compare their experiences. A failed monsoon in India, floods in South America, fires in Indonesia, a strange season of storms in the Central Pacific. For a long time, these events were treated as separate stories. Each had its own local explanations and superstitions. It took systematic record-keeping and a few stubborn minds to connect the dots. In the early 20th century, scientists began to notice that when atmospheric pressure rose in one side of the Pacific, it tended to fall on the other side. This seesaw in pressure between the western and eastern Pacific became known as the Southern Oscillation. When researchers compared this pattern with ocean temperature records and reports from fishermen, they realized they were looking at different faces of the same creature. Today, we treat the El Niño Southern Oscillation as a single system. Warm water pools in different places, trade winds strengthen or weaken, clouds and rainfall shift their usual positions. The cycle does not run on a perfectly regular schedule, yet over longer periods it averages a few years between peaks. Sometimes the warm phase barely nudges the climate out of its normal groove. Other times, as in the late 1990s and again in recent decades, it rises like a cresting wave and breaks over the entire planet. When that happens, We do not need delicate instruments to know something is off. We feel it in drained reservoirs, flooded streets, smoky sunsets, and disrupted harvests. If you are listening to this and thinking about your own home, your mind might already be mapping these stories onto your own memories. Maybe you recall a winter that refused to arrive on time, or a summer where the nights never seemed to cool down. Perhaps news about coral bleaching or Amazon fires felt like background noise, unrelated to your daily routine. Now imagine that these seemingly separate events are beads on the same thread. The question is not only how often this thread will tug on our lives, but how that tug is changing as the entire planet warms. This is where the idea of cycles becomes both comforting and dangerous. On one hand, knowing that Earth has long swung between different states can make our current extremes seem like just another chapter in a very long story. People sometimes use that logic to downplay the urgency of climate change. They point to ice ages and warm periods in the past and say that the planet has always changed, so we should simply ride this out. On the other hand, a closer look at the timing and speed of those changes reveals a more unsettling truth. Many natural cycles take thousands or tens of thousands of years to complete a full swing. The most recent jump in global temperature has happened in about 100 years. El Niño and its counterpart La Niña live in this uncomfortable middle ground. They are not human inventions, and they have been shaping regional climates for at least tens of thousands of years. They appear in coral records and sediment layers that long predate industrial smokestacks. Yet the background against which they now operate is different. The baseline ocean and atmosphere are warmer, ice is retreating, heat waves start from a higher floor. When a strong El Niño warms the Pacific today, it does so on top of a planet that has already been heated by human activity. That means the same pattern can produce more intense outcomes than it would have in a cooler world. You can think of it like a tide coming in under a set of waves. The waves themselves follow patterns driven by winds and distant storms. The tide is the slower rise and fall of the whole sea. If the tide comes in far enough, even normal waves can start reaching places they never touched before. In the same way, natural cycles like the El Niño Southern Oscillation are still sending their waves through the climate system, but the human-driven rise in greenhouse gases has lifted the entire background level of heat. That raises an uncomfortable question. When the next strong El Niño arrives, exactly how high will its waves reach? We are going to spend a lot of time with that question, because it cuts through the noisy argument about whether change is natural or human-made. The honest answer is that both matter. Ancient cycles continue to operate, but our emissions have tilted the stage on which they perform. Before we can see how that tilt plays out in detail, we need a solid picture in our minds of how the climate behaves when everything is closer to balanced. That means building a mental model of the planet as a heat engine, driven by sunlight, shaped by air and water set into motion. To really judge how strange our current weather has become, we first need to understand how it is supposed to look when the machine is running smoothly.
Sunlight is not spread evenly. The equator is the hottest place on the planet. The poles are the coldest. The tropics are the wettest. The deserts are the driest. The mountains are the windiest. The oceans are the wettest. The forests are the greenest. The cities are the loudest. The farms are the most productive. The animals are the most diverse. The plants are the most beautiful. The people are the most creative. The world is a beautiful place. Sunlight is not spread evenly. The equator faces the sun more directly and for a longer part of the year, so it receives more energy. The poles sit at an angle, so light arrives more slanted, spread over a larger area and filtered through more air. Right away, that creates a simple rule. The tropics are usually warm and the poles are usually cold, and everything in between is trying to move heat from one end to the other. Now take that simple picture and tilt it. Earth is not straight up and down relative to its orbit. Its axis is tilted a little bit, like a spinning top leaning as it turns.
Days grow longer and the sunlight is more direct. We call that summer. When your half leans away, your days shorten, the sunlight grazes in at a shallower angle, and the air cools. We call that winter. The magic of this tilt is that it creates seasons without changing the total amount of energy arriving at the whole planet very much. Earth as a whole gets roughly the same sunlight in January as in July. What changes is where that energy lands and how concentrated it is. That is why you can have snow in one hemisphere while the other bakes in heat, even though the sun itself has not changed. It is like a slowly turning spotlight sweeping across a stage, brightening one side while dimming the other, yet shining with the same power overall. If the story stopped there, your local weather would simply be a matter of latitude and calendar date. Closer to the equator, always warm and often wet. Closer to the poles, always cold and often dry. Summers and winters marching back and forth in a predictable pattern. But the climate system is not a stack of still layers. Air and water move. Once you let them move, the world you know comes into focus. Warm air is light, cold air is heavy. When sunlight heats the ground in the tropics, the air just above it warms and becomes buoyant. It rises, expands and cools as it climbs. Higher up, that cooled air eventually spreads sideways toward the poles. As it moves away from the hot equator, it cools further, becomes heavier again, and sinks back down. Near the surface, that sinking air flows back toward the equator to replace what was lifted. You can picture this as a giant loop of air, rising near the equator and falling back down a little farther away. In reality, because the planet is large and rotates beneath this moving air, that simple loop breaks into bands. The largest of these are called Hadley cells, great overturning rolls of atmosphere that dominate the tropics and subtropics. Near the equator, rising air fuels towering thunderstorms and heavy rain over warm oceans. Farther north and south, where that air has drifted away and sunk back down, the surface becomes dry. Many of the world's deserts, from the Sahara to parts of Australia, sit under these sinking branches, where clear skies and dry air are the norm. As air flows within these cells, it does not move straight north or south. Earth is spinning. That spin deflects moving air sideways, a twist known as the Coriolis effect. Near the surface in the tropics, this deflection turns the returning flow toward the west, creating steady trade winds that blow from east to west. For centuries, sailors used these winds like conveyor belts. Today, they still help drive the great piles of warm water in the Western Pacific and Indian Oceans, and they control where clouds form and where they disappear. Higher up, the air that has risen and moved poleward can form powerful bands of faster wind. These are the jet streams, narrow rivers of air racing from west to east. They snake around the globe, guided by temperature contrasts between warm and cold regions. Jet streams matter because they steer storm systems. A slight wobble in their path can mean the difference between a storm passing harmlessly north of you or stalling overhead and dropping weeks' worth of rain in a few days. When you hear that a storm track has shifted, what you are really hearing is that these upper-level winds have changed course. Beneath the atmosphere, the oceans are also constantly in motion. At the surface, winds drag on the water, setting it in motion. Over time, this creates wide gyres, looping currents that swirl in each major ocean basin. Warm water tends to flow away from the equator along the western edges of continents, then cool and return along the eastern sides. The Gulf Stream in the Atlantic, for example, carries warm water from the tropics toward Europe. That warmth is part of why cities at high northern latitudes, such as those in Western Europe, feel milder than other places at similar latitudes in North America. This slow oceanic conveyor does another crucial job. Water has a much higher heat capacity than rock or air. It can absorb a lot of energy before it warms up, and it releases that energy slowly. So while land surfaces heat up and cool down quickly, the oceans smooth out those swings. They act as giant batteries for the climate system, charging up during long sunny seasons and discharging heat back into the air during colder months. This is one reason coastal regions often have milder climates than inland areas. The sea damps the extremes. Put all of this together and you begin to see the planet as a linked machine. Sunlight pours in, most directly at the equator. Air rises, moves, and falls in great overturning loops. Winds push surface waters into currents, which carry heat across basins and between hemispheres. Temperature contrasts carve fast-moving jet streams into the upper atmosphere, which in turn shepherd storms along preferred paths. Ice and snow reflect sunlight back to space, while darker oceans and forests absorb it. Vegetation breathes carbon dioxide and water vapor into the air, changing how much heat the atmosphere holds. Every piece talks to the others. What we usually call a stable climate is not a frozen, unchanging state. It is more like a jazz band that has found a groove. There is constant motion, constant exchange of energy, but the patterns stay within a familiar range. Summers might be hotter some years and milder in others. Winters might deliver one memorable blizzard and then a run of gentle storms. Farmers, city planners, and ecosystems quietly adapt to that range. Crops are planted according to typical frost dates. Buildings are designed for expected snow loads and wind speeds. Forests grow with a mix of species that have, over many generations, fit themselves to what the weather usually does. You can feel this expectation even if you do not think about it. You have an internal calendar of what your hometown weather should be like. You know roughly when the first warm days of spring tend to arrive and when the leaves usually fall. You know what a normal summer thunderstorm looks and feels like, and how often you expect to see one. This unspoken sense of normal is your personal version of climate. It is built from memories and stories, but beneath those memories lies the physical machinery we have just walked through. Now imagine gently nudging that machinery, not by slamming it with an asteroid or turning off the sun, but by slightly changing one of the controls that sets the overall conditions. Maybe you change the way Earth orbits the sun, shifting how much light different latitudes receive over long stretches of time. Maybe you release more heat-trapping gases into the air, so that the same amount of sunlight is held more effectively at the surface. Maybe you tilt the axis a little more or a little less. In theory, these sound like small adjustments, but because everything in the system is connected, they can start chains of events. For example, a very slight change in solar energy reaching northern high latitudes over thousands of years can allow snow to linger a bit longer each spring. Snow reflects more sunlight than bare ground. As more light bounces back to space, less is absorbed as heat. That can keep things cooler, which allows more snow to survive the following summer. Over time, snowfields grow into ice sheets. The world brightens from space, reflecting even more sunlight, and the pattern feeds on itself. What began as a gentle change in orbit becomes a full-blown ice age. The machine finds a new groove, colder and icier, but still a groove. On the flip side, if snow and ice retreat, darker ground and water take their place. Those darker surfaces absorb more sunlight and warm further. This positive feedback can help the planet climb out of deep freezes and into warmer states. None of this happens overnight. These are slow stories, written over tens of thousands of years. Yet they remind us that the climate machine is sensitive to small pushes, especially when those pushes are applied in the same direction for a long time. Shorter-term imbalances can be just as revealing. A small shift in the usual trade winds can change where warm water piles up in the Pacific. That in turn moves clouds and rain belts, which affects where crops flourish and where they fail. A modest wobble in the jet stream can trap a heat dome over one region and a rain-soaked trough over another. For most of history, such variations stayed within a band that ecosystems and societies could handle, even if individual years were harsh. A bad harvest might be followed by a good one. A damaging flood might be followed by a decade of calmer rivers. This is why scientists draw such a sharp line between weather and climate. Weather is the day-to-day expression of the machine. It is the storm that hits your city, the frost that kills your garden, the fog that cancels your flight. Climate is the statistics of all those events stacked together over decades. It is the typical range of temperatures in your region, the usual timing and amount of rainfall, the odds of extreme events. You could think of weather as single notes, and climate as the melody they form when you listen long enough. For you as a person living inside this system, both matter. Weather shapes your immediate decisions. Do you carry an umbrella today? Do you shelter in place when a hurricane approaches? Climate shapes the deeper structure of your life. What crops are viable where you live? How much insulation your house needs? Where cities choose to build and where they avoid building. The more we learn about the physical machinery of the climate, the better we can see when the melody itself is changing, not just the notes. A key question then becomes, what does a healthy range of variation look like for this planetary machine? If we could watch Earth over hundreds of thousands of years, what patterns would repeat reliably, and which swings would stand out as exceptional? Scientists have built their answer by digging into ice cores, ocean sediments, tree rings, and other natural archives. These records let us see how often ice advanced and retreated, how greenhouse gas levels rose and fell, and how warm or cold different eras really were. Before we dive into those ancient stories, it is worth pausing with one thought. The same machine that gave you your personal sense of normal weather has also carried the planet through ice ages and warm periods that would make your entire hometown unrecognizable. The bands of rising and sinking air, the trade winds, the ocean currents, the jet streams, the reflective ice sheets and dark forests. They were all there in some form as the world swung between very different states. What changed were the slow background pushes that nudged the whole system toward more ice or less. Right now, in your own lifetime, we are applying a new kind of push. Instead of slowly shifting the orbit or tilt over many thousands of years, we are changing the composition of the atmosphere in a handful of generations. That change does not stop the natural cycles from turning. It layers an extra force on top of them. To grasp what that means, we need to understand how the climate machine has behaved during past swings and how quickly those swings have played out without our help. Only then can we see clearly how unusual the pace of the current shift really is. To do that, we have to leave the world of human calendars and written history behind and step into the deep time records where the planet has kept its own diary. If we want to see how the climate machine behaves over its full range, we have to read a diary that no human wrote. Ice, mud, and stone have been keeping track of temperature, greenhouse gases, and ocean chemistry for far longer than our species has existed. The trick is learning how to read them. When snow falls in polar regions, it traps tiny bubbles of air and delicate layers of dust. Over time, that snow compresses into ice. Each layer holds a sample of the atmosphere from the time it fell. Drill down through hundreds or thousands of meters of ice, and you are literally moving backward in time, year by year, storm by storm, freeze by thaw. Scientists melt and analyze that ice to measure ancient levels of carbon dioxide, methane, and other gases. They also look at the ratios of different forms of oxygen and hydrogen in the water molecules themselves. Those ratios shift with temperature, so they become a kind of built-in thermometer. The deeper the ice, the older the air, and the older the temperature record. In places like Antarctica and Greenland, these cores stretch back hundreds of thousands of years. When you line up all those measurements, you do not see a flat line, you see a heartbeat. That heartbeat is the sequence of ice ages and warm periods that has dominated the last few million years. In the cold phases, massive ice sheets grow over North America, Europe, and parts of Asia. Sea level falls as water is locked up on land. In the warm phases, those ice sheets melt back, sea level rises, and the climate in many regions becomes wetter and more temperate. On a graph, the temperature curve climbs and falls like a slow breathing pattern. The rises and drops are several degrees Celsius in global average terms, much larger than the change you have personally felt so far. Yet what really stands out is the timing. These swings are not random. Many of them line up closely with slow, predictable changes in Earth's orbit and tilt, known together as Milankovitch cycles. These cycles describe three main motions. First, the shape of Earth's orbit around the Sun slowly shifts from more circular to more stretched and back again. This changes how much the planet speeds up and slows down during its yearly path, and slightly changes the total energy it receives. Second, the tilt of Earth's axis itself wobbles between slightly smaller and slightly larger angles. That tilt sets how strong the seasons are in each hemisphere. Third, the direction in which the axis points slowly traces a circle in space, like a spinning top whose point of contact moves. That alters which part of the orbit lines up with which season. None of these motions are dramatic by themselves. The total amount of sunlight the planet receives changes only a little. What does change more strongly is how that sunlight is distributed in latitude and season, especially at high northern latitudes where the big ice sheets can grow. Slightly cooler summers in those regions means snow is less likely to melt completely. If snow survives from one year to the next, it piles up. Over many generations, that snow compacts into ice and spreads. More ice means more reflection of sunlight, which cools things further and encourages even more growth. You can feel the feedback building. The ice cores confirm that when orbital conditions favour cool northern summers, ice sheets gradually advance and the planet enters a glacial phase. Global temperatures fall, greenhouse gas levels drop, and the whole climate machine settles into a colder groove. When the orbital setup flips to favour warmer summers, the balance tips the other way. Ice sheets retire, sea level rises, and the climate warms back toward an interglacial phase like the one we live in now. The change is not instant. It can take many thousands of years for ice sheets to build or melt fully. Yet across hundreds of thousands of years, the rhythm is clear enough that it convinced many early skeptics that these cycles are real drivers, not coincidences. Ice cores are only part of the story. Far from the poles, the ocean floor collects its own time series. Tiny organisms in the surface ocean build shells from calcium carbonate, using oxygen drawn from seawater. When they die, their shells fall to the bottom and accumulate in thin layers of mud. By drilling into those sediments, scientists can reconstruct ocean temperatures and ice volumes from isotopes in the shells. These records stretch even farther back than the ice, in some cases tens of millions of years. They reveal not only the recent dance of ice ages, but also older climates where there were no large ice sheets at all. In those ancient warm worlds, tropical plants grew at higher latitudes than they do now. Crocodile-like reptiles swam in waters that are now near the Arctic Circle. Sea level stood tens of meters higher. There were long stretches where atmospheric carbon dioxide was much higher than pre-industrial levels. The planet did not fall apart in a single instant, but it looked and felt profoundly different. Forests grew where there is now tundra, shallow inland seas covered what are now plains. The positions of continents were different too, which changed ocean currents and wind patterns. All of this reinforces a simple point. Earth's climate machine has many stable states. The one you know is only one of them. Sometimes the transitions between these states are smoother. Other times they contain brutal jumps. One of the most famous is the end of the last ice age. As the world slowly warmed, a period of rapid cooling known as the Younger Dryas interrupted the climb. Temperatures in parts of the northern hemisphere fell sharply back toward glacial conditions for about 1,000 years. Then, just as quickly in geological terms, they snapped back to warming. The leading ideas to explain this event involve sudden changes in how fresh water entered the North Atlantic, disrupting a major ocean circulation loop. It is a reminder that the climate system can respond in sharp steps, not just gentle slopes, when key parts of the machinery are jolted. There are even older episodes where the system appears to have been pushed very hard. Roughly 56 million years ago, during an event called the Paleocene-Eocene thermal maximum, global temperatures spiked in a relatively short time. The exact cause is still debated, but evidence points to a massive release of carbon into the atmosphere and oceans. This could have come from volcanic activity, large deposits of methane, or both. The pulse ended. It took the planet a long time to recover. The pulse was a rapid warming that lasted tens of thousands of years and altered ecosystems around the world. Many deep-sea species went extinct. Tropical conditions pushed poleward. After the pulse ended, it took the planet a long time to draw down the excess carbon and cool back toward its previous baseline. Another class of dramatic events are the so-called snowball Earth episodes, when it appears that ice may have extended close to the equator. During these periods, reflective ice covered so much of the surface that the planet bounced a large fraction of sunlight back to space. Once such a state is reached, the usual feedbacks that cool the planet become very strong. The escape route likely came from volcanic carbon dioxide building up in the atmosphere over millions of years, eventually providing enough greenhouse effect to overcome the ice and start melting it back. When the ice finally retreated, the shift toward a warmer state could have been abrupt and extreme. Looking at all this, you might feel a strange mix of reassurance and alarm. On one hand, the climate system clearly has ways to recover from big pushes. Earth did not stay locked in a single state forever. On the other hand, the pushes that caused some of those past shifts were enormous in scale and unfolded over time spans that make human history look tiny. The important piece for our story is not just the size of the changes, but the speed. When scientists analyze how quickly temperatures rose or fell in different events, they often find that even the more abrupt natural swings still played out over many centuries or longer. That is why the ice core record of the last 800,000 years is so striking. Each glacial cycle in that period shows a pattern. Temperatures and greenhouse gas levels fall slowly into an ice age, then rise more quickly into a warm interglacial, then drift downward again. The full cycle takes tens of thousands of years. Against that backdrop, the rise in greenhouse gases and temperature over the past century is a vertical line. Human emissions have pushed carbon dioxide from pre-industrial levels to modern levels in a few generations. Global average temperature has followed suit with a sharp climb. On the graphs, this recent spike looks almost like a glitch, until you realize that you are living inside it. You can think of deep time as a long film of the climate machine, running in many different configurations. If you play that film fast, ice sheets grow and shrink, ocean currents drift and reorganize, deserts expand and contract, forests march north and south. Then, right at the end of the reel, there is a flash where a new force appears, one that does not come from orbital cycles or slow tectonic shifts. That force is industrial civilization releasing fossil carbon at a rate the natural system is not used to. The film has not yet finished, so we do not know exactly how this scene ends, but we can already see that the slope of change is steeper than most past events. It is tempting for people to look at this history and ask a simple question. If climate has swung so wildly before, why worry now? Did not past life forms endure ice ages and hothouse periods without power plants and climate agreements? The answer is that life, taken as a whole, is remarkably resilient, but individual species and societies are not. Many species went extinct during past transitions. Entire ecosystems reorganized over thousands of years. Human civilization, from agriculture to megacities, has emerged during a period of relative climate stability that is actually quite special. We have built our infrastructure and economies tuned to that stable range. Another important point is that while the planet eventually finds a new balance after large disturbances, that new balance might not include coastline locations or climate zones in the same places. For a coral reef, 10,000 years might be enough time to adapt, or for new reefs to form elsewhere. For a coastal city, 10,000 years is not a useful planning horizon. Our challenge is less about the ultimate state of Earth many millennia from now, and more about the speed and scale of change over the next few centuries, the window in which your children and their descendants will live. Deep time also helps us see that natural cycles and human-driven change are not opponents, they are layers. Milankovitch cycles continue to turn. The planet will still wobble and shift its orbit. Over very long periods, continents will continue to drift, mountain ranges will rise and erode, and ocean basins will open and close. On top of this slow backdrop, faster natural rhythms like the El Niño southern oscillation and the dynamics of the polar vortex will keep modulating regional weather. Our addition is another layer of forcing that acts faster than most of the others. Right now, that extra layer is raising the baseline temperature and altering the composition of the atmosphere and oceans. In physical terms, we are adding more energy to the climate machine and changing how easily that energy can escape back to space. In everyday terms, we are turning up the background heat on the stove while the pot is already simmering with natural cycles. The deep time record warns us that when the system receives a sustained push, it can respond in non-linear ways. Ice can collapse more quickly than it grew. Currents can reorganize rather than just speed up a little. Feedback loops can kick in and amplify the first nudge. This is why the question of pace matters so much. A slow change gives ecosystems and human societies more time to move, adapt, and reinvent themselves. A rapid change compresses those demands into a few lifetimes. The ice cores and sediment records tell us that the current spike is fast. The orbital cycles and deep climate history tell us that the system has thresholds and tipping points. The combination should pull our attention. It moves the debate beyond abstract arguments about whether climate has changed before, and into a more concrete question. How comfortable are we forcing the machine toward parts of its parameter space that human beings have never experienced? Hold that question for a moment, because it will guide everything that follows. We have seen that Earth's orbit and tilt can steer the climate into ice ages and warm interglacials over long stretches. We have seen that massive natural releases of carbon can trigger sharp warming events that take tens of thousands of years to settle. Now we are living through a new experiment where the source of the push is us, and the timeline is measured in decades rather than millennia. To understand what that means in practical terms, we need to zoom back in from millions of years to the narrow slice of time in which settled human life has unfolded, and watch what happens when that. Picture the moment when the Ice Age curtain lifts for the last time and the world steps onto a new stage. Glaciers retreat from large parts of North America and Europe. Sea levels rise and then slow. Temperatures settle into a relatively stable range that is neither as cold as the glacial deep freeze nor as hot as ancient hothouse worlds. This new phase, which scientists call the recent interglacial, lasts for about 10,000 years and counting. It is during this quiet, temperate stretch that your entire recorded history unfolds. In this calmer climate, seasonal rhythms become predictable enough for something revolutionary to happen. Instead of roaming after herds and wild plants, people in several regions begin to experiment with staying put. In the Fertile Crescent, in parts of China, in Mesoamerica and elsewhere, communities start to plant seeds and deliberately tend crops. They domesticate animals. Permanent settlements grow into villages, villages into cities, cities into networks of trade. Writing appears, laws, art, religion, and technology accelerate. All of this depends on a simple background condition. The seasons, while variable, stay within a band that crops and livestock can survive. If the climate swung wildly every few decades, agriculture would be far harder. You can see hints of this dependence in stories of ancient droughts and floods that toppled early kingdoms. Yet over the broad sweep of the last several thousand years, the global climate flickers rather than lurches. There are multi-decade shifts, like the warmer conditions in parts of the North Atlantic region around 1,000 years ago, and cooler centuries, like the so-called Little Ice Age, that brought harsher winters to Europe and parts of North America. These variations matter locally, but they ride on top of a relatively stable global average. The film of human history plays out on a climate stage that is steady enough for agriculture and cities to adapt. That stage is not static, though. Even before large-scale industry, humans begin to modify landscapes in ways that nudge the system. Clearing forests for fields changes how much sunlight is reflected, and how water moves through the soil. Early rice agriculture and livestock release methane, another greenhouse gas. Some researchers argue that these activities may have slightly altered greenhouse gas levels over thousands of years. Still, compared to what comes next, these early influences are small ripples rather than a wave. The climate machine stays in a groove that, from a bird's eye view, looks almost flat. Then, in a tiny sliver of time near the right edge of the graph, the line bends. It begins with coal. In the 18th century, people in parts of Europe start to dig up this ancient compressed plant matter and burn it in large quantities for heat and power. James Watt and others refine steam engines that can turn that heat into mechanical work. Textile mills, trains, ships, and eventually factories burn more and more coal. Later, oil and natural gas join the mix, feeding cars, planes, electricity grids, and chemical industries. Each ton of fossil fuel burned takes carbon that was locked underground for millions of years and releases it into the modern atmosphere. At first, hardly anyone notices anything beyond smoke and local air pollution. The idea that this invisible gas could someday warm the planet remains mostly a curiosity. In the late 19th century, a few scientists calculate that increasing carbon dioxide should trap more heat, but the world is not yet listening. The emissions, however, keep rising. By the middle of the 20th century, the scale of fossil fuel use explodes. World wars, reconstruction, and a wave of industrialization drive energy demand higher. Cars and trucks spread across continents. Power plants sprout near every major city. In the middle of the 20th century, a scientist named Charles Keeling begins a careful series of measurements of carbon dioxide at an observatory high on a Hawaiian volcano. Far from local pollution sources, the air there gives a clearer picture of the global background. His instruments record a steady upward climb year after year, with a gentle sawtooth wobble as plants in the northern hemisphere breathe in during growing seasons and release carbon during winters. That rising staircase of data becomes one of the most famous graphs in climate science. It shows that carbon dioxide is not just drifting up a little, it is climbing at a pace the ice cores tell us is unprecedented in hundreds of thousands of years. Before large-scale industry, carbon dioxide levels were roughly in the high 200s of parts per million. Today, they are well over 400 parts per million and still rising. That may sound like a tiny fraction of the atmosphere, and it is, but this trace gas has an outsized effect. Without natural levels of greenhouse gases trapping heat, Earth would be a frozen world. Adding more is like thickening a blanket. The sun still provides the same energy, but less heat escapes back into space. The planet must warm until a new balance point is reached, where outgoing heat again matches incoming sunlight. The physics behind this is not new, it is the same basic greenhouse effect that has been understood for more than a century. What is new is the rate at which we are changing the concentration of these gases. The ice cores show that past natural rises in carbon dioxide during the end of ice ages unfolded over thousands of years. The modern rise has happened in a handful of generations. If you graph the last 800,000 years of carbon dioxide from ice cores and then extend the line with modern measurements, this century looks like a spike. It is so steep that on some scales it barely fits on the page. Temperature has followed. Since the late 19th century, global average surface temperatures have risen by roughly 1 degree Celsius. That average hides larger changes in some places and seasons. The Arctic has warmed much faster. Heat waves in many regions now reach higher peaks and last longer. Nights have warmed more than days, which is a fingerprint of greenhouse gas-driven change, rather than just more intense sunlight. The upper atmosphere has cooled in certain layers even as the surface warms, another sign that the extra trapping is happening lower down, rather than from increased solar output. If you are picturing local weather swings, it might be hard to feel that single degree. Some winters still bring harsh cold. Some summers feel milder than others. This is where the difference between notes and melody becomes important again. Climate scientists are not claiming that every hot day is caused by emissions, or that cold days have vanished. They are pointing out that the statistical distribution of temperatures has shifted. There are more hot days on the warm side of the curve and fewer cold days on the cool side. Extremes that were once considered rare are now showing up more often. Critics sometimes argue that this might still be within the range of natural variability. This is where deep time helps. The combination of modern instrument records, tree rings, corals, and ice cores provides a reconstruction of global temperature over the last 1 or 2,000 years. That reconstruction shows gentle ups and downs, including the warmer and cooler phases people sometimes cite. Then, at the far right, the line shoots upward. This pattern has been called a hockey stick because of its long, relatively flat handle and sharp, upturned blade. That shape is not just an artist's choice. It reflects a real departure from the range of recent natural variation. The question then becomes, could this spike be driven by something other than our greenhouse gas emissions? Researchers have checked other suspects. Changes in solar output have been measured by satellites and inferred from older records. Although the sun does vary, the magnitude and timing do not match the modern warming. Volcanic eruptions tend to cool the planet in the short term by injecting reflective particles into the stratosphere. Orbital cycles act far too slowly to explain a jump in 1 or 2 centuries. When you plug these factors into climate models without human emissions, they cannot reproduce the observed warming trend. When you add greenhouse gas emissions from fossil fuels, cement production, and land use changes into the models, the picture changes. The simulated temperatures track the observed rise much more closely. The spatial patterns also match better. Land warms faster than ocean. High latitudes warm faster than the tropics. Nights warm more than days. Winters warm more than summers in many regions. Ocean heat content rises, which we can confirm with millions of measurements from buoys and ships. These multiple lines of evidence converge on the same conclusion. Human activities are now a major driver of the climate machine. The numbers involved are sobering. Every year, humanity currently releases tens of billions of tons of carbon dioxide into the air. That is like adding a layer of insulation that grows thicker with each passing year. The oceans absorb a large share of this extra heat, slowing the rise in surface air temperatures, but at a cost. Warmer water expands, contributing to sea level rise. Extra carbon dissolves into seawater, making it more acidic and putting stress on shell-forming organisms and coral reefs. Land ecosystems also take up some of the carbon, but as forests are cleared or burned, that capacity is reduced. From the perspective of deep time, this is a massive energy injection delivered on a very short schedule. Remember the event 56 million years ago when a big burst of carbon led to rapid warming that lasted tens of thousands of years? The rate of carbon input today is likely comparable or even higher, compressed into a much shorter time. That does not guarantee the same exact outcomes because the continental layout and background conditions are different, but it does remind us that the system is capable of large responses to carbon shocks. You might wonder where natural cycles fit into this picture now. After all, the orbital rhythms that have paced ice ages are still operating, even if their influence unfolds slowly. Calculations suggest that, without human interference, the current orbital configuration might have led to a gradual cooling trend over the next many thousands of years, potentially setting up another glacial advance far in the future. Instead, we see warming. It is as if the natural hand on the thermostat was slowly nudging the dial toward cool, and we came in and yanked it sharply toward warm. Other internal cycles, like the El Niño southern oscillation and the dynamics of the polar vortex, still create year-to-year and decade-to-decade flickers on top of the rising trend. In some years, a strong La Niña can temporarily slow the rate of surface warming by burying more heat in the deep ocean. In others, a strong El Niño can give global temperature a visible bump as warm water spreads across the Pacific. These ups and downs sometimes fuel confusion. People see a few cooler years and wonder if the warming has paused. Then a strong El Niño arrives and global averages jump, reminding us that the underlying trend never went away. This interplay between a rising baseline and natural swings is a key part of our story going forward. It is not that human-driven warming has replaced all other climate rhythms. It has, instead, changed the background on which those rhythms play. Strong El Niño events now occur in a world where average sea surface temperatures are higher. Heat waves linked to persistent high-pressure systems start from a warmer starting point. Rainfall extremes, droughts, and storm behaviour are all influenced by both the natural cycles that still turn and the extra energy we have added. Here is where the pace of change comes back to your personal scale. The spike in greenhouse gases and temperature is unfolding within a few human lifetimes. Many people alive today have seen a meaningful shift in climate within their own memory. Farmers notice planting seasons creeping earlier. Ski resorts track shrinking snowpacks. Coastal communities watch high tides lap closer to roads and homes. These are not distant, abstract graphs. They are signals that the stable groove we relied on is being reshaped quickly. We are standing at a moment where the long, slow cycles of deep time continue to turn quietly in the background, while a sudden, human-driven spike is rewriting climate patterns on the timescale of news cycles and lifetimes. To understand how this new background interacts with the shorter rhythms that still govern year-to-year weather, we need to look more closely at one of the strongest of those rhythms, the one we first met earlier. It is the Pacific seesaw, whose warm and cool phases can tilt rainfall, heat, and storms across whole continents. And on a warming planet, each time that seesaw tips, the consequences reach a little farther. Stand on a beach somewhere along the equator in the Pacific on a typical year, and you are standing on top of the engine room of the world. The sun beats down almost straight overhead. Trade winds blow steadily from east to west, pushing the sun-warmed surface water into a thick pile in the western Pacific, near Indonesia and northern Australia. There, the sea surface stands literally higher than in the east, a warm pool of water several degrees hotter than the cooler tongue that clings to the coast of South America. Above this contrast, the air and clouds arrange themselves into a pattern that, when it holds, gives much of the planet its familiar rhythm. Under neutral conditions, warm water in the west fuels rising air and deep thunderstorms. That rising plume of warm, moist air feeds a band of towering clouds, often seen on satellite images as a bright stripe near Indonesia. High above, the air that has risen spreads eastward, then slowly descends over the cooler eastern Pacific. Near the surface, the trade winds complete the loop, blowing from east to west, pushing more water toward the warm pool. At the eastern edge, near Peru and Ecuador, those winds help pull cold, nutrient-rich water up from the depths in a process called upwelling. Cold water rises, feeds blooms of microscopic life, and supports rich fisheries. If you picture this pattern sideways, it looks like a huge atmospheric conveyor belt spanning half the planet, with warm air rising in the west and sinking in the east. Scientists call this the Walker circulation. It is one of the reasons the western Pacific tends to be stormy and wet, while the eastern tropical Pacific and the coastal deserts of South America tend to be drier. As long as this circulation and the trade winds that drive it stay strong, the Pacific acts like a tilted bathtub, water piled warm and deep in one corner, cool and shallower in the other. Now imagine nudging that balance. For reasons that involve both random atmospheric jostling and deeper ocean processes, the trade winds sometimes weaken. When they do, they stop herding quite as much warm water toward the west. Some of that stored heat begins to slosh back eastward along the equator. At the same time, the upwelling of cold water in the eastern Pacific slows down. Without that steady supply of cold water from below, the surface there starts to warm. Over weeks and months, a tongue of warmer than normal water spreads across the central and eastern tropical Pacific. From orbit, this change appears as a smear of red on maps of sea surface temperature, where there would normally be blues and greens. On the ground and at sea level, clouds and rainstorms drift eastward with the warm water. Regions that usually sit under clear skies see more cloud cover and heavier rain. Regions under the normal storm track can quiet down. This is the onset of El Niño, the warm phase of the cycle. What began as a subtle loosening of the trade winds becomes a full reorganization of tropical weather. Because the tropics are the main source of heat and rising air for the whole atmosphere, that reorganization sends ripples outward along jet streams and storm tracks. In the opposite situation, the trade winds strengthen beyond their usual pace. They push even more warm surface water into the western Pacific and north of Australia, causing sea levels there to rise a little higher and warm water to pile deeper. In the eastern Pacific, stronger winds encourage more upwelling. Cold, deep water wells up to the surface over a broader area, reinforcing a wide tongue of cool sea surface temperatures stretching along the equator. Thunderstorm activity concentrates even more tightly over the far western Pacific. The east grows clearer and drier. This is La Niña, the cool phase. El Niño and La Niña are not just mirror images. Each phase bends the normal climate in different ways. During El Niño, warmer surface water in the central and eastern Pacific pumps extra heat and moisture into the atmosphere there. This tends to shift the main band of tropical rain, which in turn tugs on the high-altitude winds farther north and south. In some regions, such as the southern United States, this can mean wetter than usual winters. In others, like parts of Australia and Indonesia, it can bring drought and a higher risk of fire. During La Niña, the strengthened trade winds and cool eastern Pacific often favour more rain over Indonesia and northern Australia, while making drought more likely in the southwestern United States and parts of South America. If this sounds abstract, it becomes painfully concrete when you walk through a strong event. Take the powerful El Niño of 1997 and 1998. In Peru and Ecuador, rainfall totals shattered records. Rivers burst their banks, washing away homes and roads. Landslides chewed through slopes that had been stable for generations. Coastal communities that depended on fishing watched their catches crash as the usual cold, upwelled water was smothered under a layer of warm, nutrient-poor surface water. The same pattern that flooded these coasts left other regions desperately dry. Across the Pacific, drought took hold in parts of Indonesia and Papua New Guinea. Forests that normally stayed damp enough to resist large fires dried to the point where a spark could unleash massive blazes. Haze from burning peat and forest hung over cities, dimming the sun and choking lungs. In some places, crop failures led to food shortages and economic stress. Farther afield, the altered storm tracks changed the behaviour of the monsoon in India and the winter storm paths over North America. Many viewers at the time experienced this event only as disjointed headlines. Floods here, fires there, a weirdly warm winter somewhere else. But step back, and the thread connecting them runs straight through the tropical Pacific. La Niña has its own trail of impacts. In the early 2000s, and again in the early 2010s, extended La Niña periods related to cooler than normal tropical Pacific waters were linked to persistent drought across parts of the western United States. Reservoirs dropped, snow in the mountains arrived late or melted early. Farmers and cities alike scrambled to manage limited water. At the same time, enhanced rainfall battered parts of Australia and Southeast Asia, leading to major floods. In some years, back-to-back La Niña events stacked their impacts, keeping regions locked in a pattern of wet or dry that stretched well beyond a single season. One of the most unsettling aspects of this cycle is how it can shift the odds of extreme events without guaranteeing them in every location. During El Niño, the likelihood of heavy rain might increase in one region, but that does not mean every El Niño year brings floods there. Local factors and other climate patterns still matter. What the El Niño Southern Oscillation does is tilt the deck. It loads the dice towards certain kinds of weather over large swathes of the planet. For farmers, emergency planners, and anyone whose work depends on climate-sensitive systems, knowing when the deck is tilted can be the difference between being caught off guard and having time to prepare. Because of this, scientists have put enormous effort into monitoring and predicting the state of the Pacific. Networks of buoys bob in the tropical ocean, measuring temperature, currents, and wind. Satellites scan the surface, watching for subtle shifts in sea level, heat, and cloud patterns. Climate models crunch all this information along with the physics of air and water to project how the cycle is likely to evolve over the coming months. These forecasts are not perfect, but they have improved enough that warnings about developing El Niño or La Niña conditions now routinely inform decisions on everything from food aid planning to seasonal hurricane outlooks. For example, when a strong El Niño began to emerge in the middle of the 2010s, agencies around the world compared current measurements to past events. They saw that surface temperatures in parts of the central and eastern Pacific were reaching levels comparable to the record-setting late 1990s event. Governments in fire-prone regions prepared for a heightened risk of blazes. Fisheries managers anticipated shifts in fish populations. Humanitarian groups looked ahead to regions that might be hit by combined drought and economic strain. Many of the impacts still hurt, but the ability to see the broad pattern coming gave some communities a chance to brace rather than be blindsided. Here is where the warming background plays its quiet but powerful role. Remember that El Niño is defined by departures from a long-term average. When the average is rising, the same departure can take you to a higher absolute temperature. A strong El Niño today means warm anomalies layered on top of an already warmer ocean and atmosphere. That means more heat available to drive evaporation, fuel storms, and stress coral reefs. The mass bleaching events that have hit reefs repeatedly in recent decades are often tied to combinations of long-term warming and El Niño spikes. A reef that might have survived a similar event a century ago can now be pushed past a threshold. On land, heat waves that coincide with certain phases of the cycle now start from a higher baseline. In some regions, droughts linked in part to La Niña occur in landscapes where soils have already been drying under higher temperatures. In others, heavy rains fall on infrastructure and floodplains that are seeing more frequent extreme events than they were designed for. This stacking of natural variability on top of human-driven warming is a theme you can watch play out again and again. It is not that El Niño or La Niña suddenly switch from harmless to dangerous. It is that the entire playing field on which they operate has been tilted. You can test this idea in your own life. Think back to a year when news about El Niño or La Niña seemed impossible to avoid. Maybe your region was warned about higher flood risk, or you saw video of distant coral reefs turning white. Ask yourself what that same pattern might look like if the baseline climate in your area continues to warm for another few decades. Would a flood that reached the steps of your local school then lap at classroom doors? Would a drought that simply browned lawns now bite deeply into food supply and forests? These are not distant hypotheticals. They are ways of translating climate jargon into lived futures. Another subtle but important aspect of this cycle is how it interacts with other large-scale patterns. The Pacific is not the only ocean with its own rhythms. The Atlantic, the Indian Ocean, and even the Southern Ocean around Antarctica have modes of variability that unfold over years to decades. Jet streams meander more or less wildly depending on contrasts between warm and cold zones. When the timing of these different patterns lines up in certain ways, their effects can reinforce each other. A warm phase in one ocean plus an El Niño can mean a double push toward heavy rainfall in some regions. A La Niña, combined with a particular North Atlantic pattern, can deepen drought. This complexity is part of why forecasting exact local outcomes remains challenging. Yet on the larger scales, the connections are strong enough that seasonal outlooks now routinely include mentions of El Niño or La Niña. When a forecast office says the coming winter is likely to be warmer and drier than average in your region because of expected La Niña conditions, they are not making a wild guess. They are leaning on decades of data showing how this Pacific seesaw has behaved in the past and how it tends to bend the odds. The question hanging over these forecasts is how those relationships will hold or shift as global warming continues. There are hints that the character of the El Niño southern oscillation itself may be changing. Some studies suggest that the pattern of warming during El Niño events has, in some decades, shifted more toward the central Pacific rather than the far eastern edge. Others argue that strong events may become more common in a warmer world, or that La Niña conditions might persist for longer stretches. The evidence is still being debated. Climate records that capture many full cycles are limited, and the system is noisy. But the very fact that scientists are asking whether this ancient rhythm is being reshaped by our influence should give us pause. Because if the background warming alters not only the impacts of El Niño and La Niña, but also their frequency or flavour, then the long-term planning built on past statistics may start to crack. Farming systems that can cope with an occasional bad El Niño might struggle under a cluster of stronger ones. Coastal communities that see flooding risk spike every few years might find the calm intervals shrinking. Emergency systems tuned to historic patterns of fire and flood may face overlapping crises. In that world, understanding and tracking these cycles is not just the job of a few specialists. It becomes part of how societies decide where to build, what to grow, and how to insure against loss. We have been following this story mostly from the warm heart of the tropics outward. Heat builds in the equatorial Pacific. Air rises, winds shift, storms march along new routes, and the consequences spill toward the mid-latitudes. But there is another way to enter the story, starting from the poles. Up there, beyond the familiar storm tracks, a different kind of circulation spins, a cold reservoir capped by fast winds that form an invisible wall between Arctic air and the rest of the world. And in recent years, that wall has begun to wobble in ways that make winters in places far from the ice feel strangely broken. Imagine flying high above the equator and heading north until the familiar bands of clouds and storms start to thin out. The air below you grows colder and drier. The sun skims lower along the horizon. Eventually, you reach a region where winter darkness can last for months, and the ground is locked under snow and ice. Up here, above the Arctic and the Antarctic, the atmosphere arranges itself into something like a spinning crown of wind. This is the polar vortex, a ring of fast-moving air that circles the pole and keeps the deepest cold more or less penned in. To picture it, imagine a huge bowl of cold, dense air sitting over the pole in winter. Above that bowl lies a layer of the atmosphere called the stratosphere, where temperatures are even lower and sunlight behaves differently. In that upper layer, strong westerly winds blow around the pole, forming a tight whirl. As long as this whirl is strong and mostly circular, it acts like a barrier. It separates the icy air in the centre from the somewhat milder air farther south. Down below, closer to the ground, weather systems and jet streams feel the influence of this spinning top, even if we cannot see it. Closer to the surface, in the lower atmosphere where storms live, the jet stream also snakes around the planet at mid-latitudes. This jet stream is driven by the contrast between warm air from the tropics and cold air from the poles. When that temperature contrast is big, the jet stream tends to be fast and more zonal, which means it flows roughly west to east, with only gentle waves. When the contrast weakens or disturbances ripple upward from below, the jet stream can slow down and meander. Its once smooth track can grow large north and south loops that pull different air masses into new places. In a typical stable winter pattern, the polar vortex remains fairly strong. The jet stream circles the globe with only modest wiggles. Cold air stays mostly bottled up over the Arctic. Mid-latitude regions feel normal winter storms, some cold snaps, some thaws, but nothing too far outside their usual range. This is the kind of winter many older residents remember as standard, even if there were always occasional extremes. The invisible wall around the pole is not perfect, yet it does its job well enough that frigid air seldom plunges deeply into densely populated regions. Every so often, however, the vortex is hit with a kind of atmospheric shock. Waves in the lower atmosphere, created by mountain ranges and large-scale weather systems, propagate upward and disturb the winds in the stratosphere. If those disturbances are strong enough, they can slow the vortex dramatically or even reverse its winds. This event is known as sudden stratospheric warming because, as the winds break down, air above the pole descends and compresses, causing temperatures in the upper atmosphere to jump by tens of degrees Celsius over just a few days. That warming high above the surface does not feel like a pleasant thaw on the ground. In fact, it often signals the opposite. When the vortex weakens or splits into separate smaller swirls, The barrier that kept Arctic air confined becomes ragged. Cold air masses that were once corralled near the pole can spill southward in lobes. A few weeks after a strong, sudden stratospheric warming, many regions in Europe, Asia, or North America can experience intense, prolonged cold spells and heavy snow. You might remember episodes where the phrase polar vortex suddenly dominated news headlines as people tried to make sense of bitter cold far from the Arctic. These events can confuse anyone who has absorbed the simple message that global warming means milder winters everywhere. People look at frozen rivers, ice-clogged streets, and power plants straining to keep up with demand and ask a natural question. If the planet is warming, why am I freezing? The answer lives in the difference between average trends and the shifting paths of air masses. Overall, winters have warmed in many regions, and extremely cold nights have become less common. But when the jet stream kinks south and a chunk of the polar atmosphere slides down with it, the local temperature can still plunge far below normal for a short time. The interesting and unsettling question is whether these disruptions are becoming more frequent or intense as the Arctic warms faster than the rest of the planet. This faster warming has a name: Arctic amplification. As sea ice shrinks, darker ocean water is exposed, absorbing more sunlight and storing more heat. In autumn and early winter, that stored heat can leak back into the atmosphere, reducing the temperature contrast between high and low latitudes. Some scientists argue that this weakened contrast can slow the jet stream and make it more wavy. A slower, wavier jet stream is more prone to getting stuck, locking regions under persistent weather patterns, whether that is cold, heat, dry, or wet. Imagine a river that normally flows fast and straight through a valley. When it slows, it begins to meander, carving deeper curves into its banks. Those curves can trap water in one region and starve another. In a similar way, a slower jet stream can dig deep troughs that allow cold polar air to surge south in some places, while ridges of warm air push north in others. Under a ridge, heat waves can bake the land and dry out soils. Under a trough, cold and storms can linger. The result is a world where extremes of both cold and heat can become more pronounced, even as the global average moves upward. You may have lived through one of these blocked patterns without realizing the role of the high atmosphere. Perhaps your town spent weeks under a heat dome where the sky stayed relentlessly blue and temperatures refused to drop at night. Or maybe a sequence of storms rolled over the same region again and again, turning streets into rivers while a neighbouring state stayed oddly dry. These are the kinds of events that become more likely when large-scale patterns slow down and stall. The polar vortex and jet stream are key pieces in that story. When the Arctic warms rapidly, and yet mid-latitude winters are relatively calm. Climate models vary in how strongly they reproduce the connection between sea ice loss, jet stream changes, and extremes. Some show a clear link, others less so. The atmosphere is a chaotic system, and teasing out cause from coincidence takes time and careful work. Still, a growing body of evidence points toward a relationship between rapid Arctic warming and an increased tendency for certain kinds of disruptions. For you, the precise balance of these mechanisms may matter less than the lived outcome. Energy grids must now be designed to handle hotter summers and, at the same time, the occasional brutal winter outbreak. Cities used to milder climates may face rare cold snaps that they are not built for, straining pipes, roads, and emergency services. Farmers must cope not only with shifting average growing seasons, but also with the risk that a late spring freeze can still sweep in and wipe out buds that opened early during a warm spell. Insurance companies track these compound risks closely because they translate into real costs. Meteorologists and climate scientists are responding by improving how they observe and model the polar regions. New satellites watch the Arctic ice cover and surface temperature. Weather balloons and ground-based instruments track wind and temperature through the full depth of the atmosphere. Supercomputers run simulations that can capture both daily storms and longer-scale swings in the jet stream. The goal is not just to predict tomorrow's weather, but to anticipate longer-range patterns, including the likelihood of sudden stratospheric warmings and the breakdown of the vortex weeks in advance. You might have noticed that the term polar vortex has become more common in media in the last decade or two. Sometimes it is used loosely to describe any winter cold snap, which can be misleading. In a stricter sense, the polar vortex is always present in winter, spinning around the pole. What matters for your experience is how strong and stable it is, and how its shifts interact with the jet stream above your region. The fact that this piece of atmospheric jargon has entered everyday language is a sign of how much more attention we are paying to the moving parts of the climate machine, especially when those parts misbehave. The bigger picture is that patterns which used to feel remote and abstract are now being felt at street level. A disturbance high over the Arctic can eventually affect whether ice forms on your local river. A patch of unusually warm ocean hundreds of kilometers away can help decide whether your city spends a winter in slush or under clear skies. As you hear more about these links, it is worth asking yourself how they might evolve as the background warming continues. If the Arctic keeps losing ice, and the temperature contrast with lower latitudes keeps dropping, will the vortex become even more prone to splits and wanderings? We have now followed two of the most important actors in this story, the Pacific seesaw of El Niño and La Niña, and the spinning crown of winds around the poles. Each is a natural rhythm, with roots that long predate industrial society. Each shapes weather across huge regions, and each is now operating on a planet where the baseline energy level is higher than it has been in the entire history of our civilizations. The real tension lies not in any one of these cycles acting alone, but in what happens when they intersect on a stage we have already tilted. When different rhythms play at once, music can become either richer or more chaotic. The climate system is no different. The slow sway of Earth's orbit and tilt keeps nudging the background over tens of thousands of years. On top of that, the El Niño southern oscillation rocks the tropical Pacific every few years. The polar vortex tightens and loosens its grip on the Arctic each winter. None of these patterns stopped when smokestacks and engines began to pour greenhouse gases into the air. Instead, they now operate in a world that is a little warmer, a little wetter in its atmosphere, and a little less frozen than before. Think of the long-term warming as raising the floor in a house, while the ceiling stays where it is. All the furniture stays in the same positions. You still have the same table, sofas, and lamps, but your head is now closer to the ceiling. When you jump, you hit it more easily. The natural cycles are the jumps. They have always been there. What has changed is how often their peaks now collide with the limits of what ecosystems and infrastructure can handle. Scientists often describe this as loading the dice. El Niño, La Niña, and polar vortex breakdowns have always tilted the odds towards certain kinds of weather in certain places. Add a degree or more of global warming, and those odds shift further. A heat wave that would once have been very rare becomes rare, then uncommon, then something you see several times in a lifetime. A rainfall event that fills rivers to the brim now overflows them. A warm spell that merely stressed corals a century ago now bleaches them outright. The cycle is the same, but the stakes attached to each phase have grown. You can watch this change in how recent strong El Niño events have played out. The El Niño of the late 1990s was, at the time, a record breaker. It helped drive unusual warmth, severe coral bleaching, fires in Indonesia, and altered storm tracks worldwide. 2 decades later, another powerful El Niño rose in the middle of a warmer baseline. Global average temperatures during that event climbed higher than during the earlier one. Coral reefs that had barely recovered were hit again. Some that had escaped major damage in the earlier event suffered badly in the later one. The cycle had not invented new physics, it was simply operating in a hotter ocean and a warmer atmosphere. On land, the pattern is similar. In some regions, El Niño conditions now stack on top of long-term drying to produce unprecedented fire seasons. In others, La Niña conditions combine with warmer air that can hold more water vapour, turning heavy rains into exceptional floods. When you hear that a region has experienced a once-in-a-century event twice in a few decades, You are hearing the echo of this loaded dice effect. Natural cycles still roll, but the faces on the dice have been repainted. At the same time, there are hints that the cycles themselves might be shifting in character. Some analyses suggest that the pattern of warming during El Niño events has, in recent decades, sometimes focused more on the central Pacific than on the far eastern edge. This subtle change can tweak which regions see heavier rainfall and which face drought. There are also studies arguing that strong El Niño and La Niña events could become more frequent as the planet warms, although this is still an area of active debate. The data record that covers many full cycles is relatively short, and the system is noisy, so clear conclusions are difficult. The polar vortex story has its own uncertainties. As we saw, Arctic amplification appears to be reducing the temperature contrast between high and mid-latitudes. Some researchers find that this is linked to more frequent or persistent waviness in the jet stream, which in turn is associated with blocking patterns and extreme weather. Others find weaker or more region-dependent links. Climate models do not all agree on the strength of this connection, yet real-world events keep nudging the question forward. Repeated episodes of deep winter cold in some populated regions, combined with simultaneous winter warmth near the pole, are hard to ignore. What we can say with confidence is that the background on which these dynamics play out has changed. The Arctic is losing sea ice, which affects how much heat and moisture are exchanged between ocean and atmosphere. Snow cover patterns on land are shifting. The upper atmosphere is being altered by greenhouse gas changes in ways that affect radiative cooling and wind structures. Even if the details of cause and effect are still being untangled, the idea that the high-latitude circulation will remain untouched by these changes does not fit what we know about a connected system. To bring this down from abstract patterns to a concrete chapter in very recent history, consider the strong El Niño that peaked in the early 2020s and then faded. During its rise, the tropical Pacific warmed sharply in the central and eastern bands. Global average temperatures jumped, setting new records in some years. Marine heat waves intensified, contributing to widespread coral bleaching in several ocean basins. Many regions saw rainfall patterns that fit the historical El Niño fingerprint, yet in some cases, the impacts were amplified by the warmer background. Heat records fell on land in ways that surprised even seasoned forecasters. As that El Niño waned, forecasts began to point toward a likely transition into La Niña conditions. On paper, that might sound like a simple flip of a switch. Warmer than usual surface waters in the eastern Pacific give way to cooler than usual patches. Trade winds strengthen, the Walker circulation tightens. In practice, this shift sets up a different pattern of risks. Regions that were flood-prone under El Niño can tilt toward drought under La Niña. Areas that were dry can swing toward heavy rain. Farmers have to pivot from worrying about waterlogging to worrying about water shortages, sometimes within only a year or two. This rapid swing between opposite phases is why some researchers talk about climate whiplash. Communities do not get to deal with one kind of stress, recover, and then rest. Instead, they move from one extreme to another before repairs and adaptations are complete. A region hammered by flood-induced landslides under El Niño might, a few years later, face wildfire risk under La Niña because vegetation regrowth changed fuel loads. Reservoirs that brimmed and overtopped can then slump toward historic lows. The same climate cycle that once brought a mix of good and bad years now interacts with the elevated baseline to produce sequences that are harder to manage. Overlay the polar story on top of this, and the pattern grows richer and more challenging. Imagine a winter when La Niña conditions favour certain storm tracks over the North Pacific, while the polar vortex is simultaneously weakened by a sudden stratospheric warming. The jet stream could meander in ways that channel cold air outbreaks into some regions and leave others under unusual warmth. In a different year, a strong El Niño could align with a tight, stable vortex, producing milder winters in some mid-latitudes, but amplifying heat and flood risk elsewhere. The possible combinations multiply. The Atlantic and Indian Oceans add further layers. The Atlantic has its own slower rhythm in sea surface temperatures that affects hurricane activity and rainfall over adjacent continents. The Indian Ocean has patterns that influence monsoon behaviour in South Asia and rainfall in East Africa and Australia. When these rhythms line up constructively with El Niño or La Niña, their joint effects can be larger. When they oppose each other, they can partially cancel. For people living under those combined influences, the resulting weather is simply what happens outside their window. But for planners, the growing complexity poses a real challenge. They must decide how much to trust past statistics in a world where both the averages and the patterns of variability are shifting. One way to think about this is to picture a map covered with overlapping, moving shadows. Each shadow is a climate influence. The slow orbital cycles change the overall lighting of the map so gradually that you hardly see it move. El Niño and La Niña cast broad, shifting bands of wetter and drier conditions across the tropics and beyond. The polar vortex and jet streams draw looping arcs of cold and heat. The Atlantic and Indian Ocean patterns add their own shapes. Human-driven warming brightens the entire map, increasing the energy in all the other shadows. When several shadows line up over the same region, that place experiences a compound event. Compound events are where much of the real-world danger lies. A coastal city might experience sea level rise from long-term warming, higher storm surge from a particularly intense cyclone season linked to ocean patterns, and heavier rainfall from a moist atmosphere all at once. An agricultural region might face a heatwave during a critical flowering period, worsened by soil moisture deficits built up over several dry years, tied partly to La Niña. An energy grid might be hit by a summer of record heat, followed by a winter cold wave triggered by a distorted polar vortex, stressing both cooling and heating systems. For individuals, these interactions show up as disruptions to things they once took for granted. Maybe summer nights no longer cool off enough for comfortable sleep without air conditioning. Maybe insurance premiums in a floodplain climb steeply, or coverage is withdrawn altogether. Maybe a favourite local food becomes more expensive as harvests become less reliable. You might hear about these changes in isolation and chalk them up to bad luck. Understanding the interplay of ancient cycles and modern warming lets you see them as part of a larger pattern. It also opens the door to anticipating some of what is coming. Agencies already use El Niño and La Niña outlooks to forecast seasonal rainfall and temperature tendencies. As models improve, they may also become better at diagnosing when the polar vortex is likely to wobble, or when ocean heat content is setting the stage for unusual hurricane seasons. Combined with knowledge of long-term warming trends, this can help guide choices about crops, water management, building codes, and energy planning. The challenge is to act on probabilities rather than wait for certainty, because by the time certainty arrives, the dice have already been rolled. At the same time, there is a humbling limit to how precise our predictions can become. The atmosphere and oceans are chaotic systems. Tiny differences in starting conditions can lead to different outcomes. Natural cycles will always retain some element of surprise. The goal is not to control the climate like a thermostat, but to reduce the size of the shove we are giving it, and to design our societies in ways that can absorb shocks without breaking. That means paying attention not only to the average warming, but also to the ways it reshapes the old rhythms we have relied on. You might find yourself wondering what this means in practical terms for the place where you live. How will shifting El Niño patterns change flooding risk in your valley? What happens to winter heating needs if polar outbreaks become less frequent but more severe when they do occur? How do farmers in your region adapt to more volatile sequences of wet and dry years? These questions move the discussion from global averages and ancient cycles to the very human scale of homes, jobs, and communities. We have spent a long time with graphs, mechanisms, and patterns that span half the planet. All of that matters because it explains why the weather you experience is changing in ways that go beyond simple randomness. But the real test of understanding comes when we ask what to do with that knowledge. Do we rebuild in the same flood zones after every disaster? Do we design cities and food systems to assume the past is a reliable guide? Or do we accept that the climate machine is now in a different state and start shaping our lives accordingly? Those are not abstract philosophical questions. They are choices that will shape how much hardship or stability people experience in the coming decades. To see them clearly, we need to bring this story down from the level of oceans and jet streams to the level of tap water, groceries, housing, health, and safety. In other words, we need to ask a simple question that cuts through the noise. Given everything we know about ancient cycles on a hotter planet, what does this actually mean for your future on this world? So what does all of this actually mean for the world you wake up in? The one with alarm clocks, grocery bills, and commutes, rather than graphs and satellite maps. It means that the background conditions you took for granted as stable are shifting under your feet. The timing of seasons, the intensity of heat, the reliability of rain, the frequency of floods and fires, they are all being nudged by a combination of ancient cycles and new warming. You are building a life on a moving platform. The question is not whether that platform moves, it always has. Do not just nudge the thermometer a little bit. Do not just nudge the thermometer a little higher. They change how often truly dangerous heat appears. When the baseline climbs, the hottest days reach further into territory where the human body strains to cope. Nights cool down less, which matters more than most people realize. Your body needs a break from heat to repair and reset. When nights stay hot, stress builds. Energy systems feel it too. Air conditioners run longer and harder, straining grids that were built for a different range of demand. Now picture that heat landing on a city built largely of dark surfaces, concrete and asphalt, that soak up sunlight and release it slowly after sunset. The urban heat island effect has always existed, but a warmer climate turns it from an annoyance into a health threat, especially for older people or those who cannot afford adequate cooling. You can already see some cities responding, with more trees, reflective roofs, and shaded public spaces. These are not nice extras, they are adaptations to a new thermal reality. The better we understand how heat waves interact with local geography and global cycles, the more precisely we can place these protections where they are needed most. Water is the other side of that coin. A warmer atmosphere can hold more moisture. That means when conditions are right for rain, there is more available to fall. Storms that would have dropped a manageable amount of water in the past can now unleash torrents that exceed the design limits of drains, levees, and dams. At the same time, between storms, higher temperatures dry out soils and plants faster, so you get a world where droughts can deepen quickly and deluges can hit hard. Natural patterns like El Niño and La Niña still tilt the odds toward wet or dry for certain regions, but the whole cycle rides on a system that swings more widely. In practical terms, that is why a flood that people call historic can now happen again within a decade, or why reservoirs can swing between too full and too empty in a few years. Towns built on river plains because they were once fertile and manageable now face levels of risk that were not part of the original deal. Some places are already making painful decisions to move neighbourhoods away from the most dangerous areas. Others are raising levees, redesigning sewers, and restoring wetlands that can absorb excess water. These are all ways of acknowledging that the old statistics no longer tell the whole story. Food is another quiet but central thread. Crops depend on reliable growing seasons and a certain sequence of rain, sun, and temperature. When those ingredients shift, yields can suffer. A heat wave during flowering can cut grain production, even if the rest of the season seems fine. A late frost can kill fruit blossoms that opened early after an unusually warm spring. Extended drought or persistent heavy rain can ruin fields that farmers counted on. Climate cycles have always influenced harvests. Strong El Niño events have long been linked to failed rains in some breadbasket regions and bumper crops in others. Now, those cycles are layered on top of a warming trend that stretches plant and animal tolerance. Farmers are already adapting in many places, often quietly, field by field. They are changing planting dates, switching crop varieties, experimenting with more drought-tolerant or heat-tolerant strains, adjusting irrigation practices. Research centres breed plants for future climates rather than past ones. Governments and insurers are slowly revising risk maps, but this adaptation is uneven. Wealthier regions have more access to technology, insurance, and backup systems. Poorer regions often feel the brunt of failed rains and extreme heat, with fewer safety nets. Understanding how ancient cycles and modern warming work together can help direct support where it is most likely to prevent hunger and conflict. The places we live are shaped by expectations about climate that often feel invisible until they are violated. Coastal cities assume a certain range of sea levels and storm surges. Mountain towns assume a certain snowpack and melt timing. Suburbs assume that wildfires stay mostly in distant forests, not at back fences. As seas rise from thermal expansion and melting ice, storm surges ride in on a higher platform. Floods that would have been close calls now overtop defences. As snowpacks shrink, communities that rely on slow meltwater pulses face longer dry periods. As heat and drought creep into new regions, the wildland-urban edge where homes meet vegetation becomes a front line for fire. Some places are beginning to retreat from the highest risk zones. Others are building seawalls, restoring dunes and mangroves, redesigning building codes to raise structures and harden them against wind and water. Planning horizons need to stretch further. A house built today may still be standing when global temperatures are higher than they are now. A bridge planned now will face storms and floods shaped by a future climate, not the one recorded in mid-20th century data. It is here that an understanding of both long-term warming and shorter cycles can be turned into something very practical. You can design for a range of futures rather than a single number. Health is another channel through which climate reaches into daily life. Heat waves increase the risk of heat stroke and worsen chronic conditions. Warmer temperatures and changed rainfall patterns can shift the ranges of disease carrying insects like mosquitoes and ticks. Air pollution episodes can worsen when stagnant high-pressure systems linger longer over cities. Wildfires, fed by drought and heat, can send smoke hundreds or thousands of kilometers, exposing millions of people to harmful particles. All of these effects can be amplified when climate cycles line up with the new baseline in unfortunate ways. For example, when a natural drought phase arrives on top of record warmth and dry soils. You might already have small rituals that reflect this new reality without naming it. Perhaps you check air quality apps during wildfire season. Perhaps you plan outdoor work earlier in the day to avoid peak heat. Perhaps you have noticed that allergy seasons feel longer. These are personal adaptations, just as city-level changes to tree cover or hospital readiness are collective ones. The more we recognise that these are not random quirks but responses to a shifting climate, the more we can make them deliberate and fair, rather than leaving them to chance or to the ability of individuals to pay their own way out of risk. Early warning systems may be one of the most powerful tools we have for living with a more volatile climate. The same science that tracks El Niño and La Niña, that monitors the polar vortex and ocean heat content, can feed into forecasts that give people time to act. A seasonal outlook that signals a high chance of drought can prompt water managers to conserve more aggressively. A warning of elevated flood risk can lead to pre-positioned sandbags, adjusted dam operations, and public awareness campaigns. Advances in weather prediction can give days of lead time before a heatwave, time enough to set up cooling centres and reach vulnerable residents. These systems are not perfect, and forecasts will always carry uncertainty. But even a probabilistic warning is better than none, especially when the stakes are high. The key is trust. People must believe that the warnings are based on solid evidence and that acting on them is worthwhile. That trust is built slowly, through consistent communication and through forecasts that prove helpful more often than not. It is eroded when signals are ignored, or when warnings are dismissed for short-term convenience. In a world where climate cycles and warming are delivering more extremes, strengthening this chain of observation, prediction, communication and action is one of the few levers that can reliably save lives. All of this raises a deeper question about responsibility and choice. Ancient cycles will continue to turn whether we act or not. The sun will rise and set. Earth will wobble and drift in its orbit. El Niño and La Niña will keep rocking the Pacific. The polar vortex will spin and sometimes stumble. Our influence is in the background level on which these patterns play out, and in how prepared we are to withstand their moods. We control how much more carbon dioxide and other greenhouse gases we add to the air. We control where we build, how we grow food, how we design energy and transport systems. Reducing emissions changes the slope of the curve. It cannot rewind the climate to an earlier state in a single generation, but it can limit how far and how fast the machine is pushed. That, in turn, can lower the odds that certain thresholds are crossed. It can make it more likely that ice sheets retreat slowly, rather than collapsing in sudden jumps, that ocean currents adjust, rather than reorganizing abruptly, that extremes become tough but manageable, rather than beyond the limits of adaptation. This is not about flipping a planetary switch from danger to safety. It is about shaping the range of futures within which communities must navigate. At the same time, we know that some level of change is already baked in. Oceans have stored a vast amount of extra heat. Ice has begun to respond. Ecosystems and economies have already felt the first waves. Adaptation is not optional. The only choice is whether it is planned and guided by science, or left to evolve in a disorderly way where the most vulnerable pay the highest price. Adaptation does not mean surrender. It means acknowledging that the climate stage has shifted and choosing to move on it with open eyes rather than pretending it is still the same. There is a temptation when faced with the scale of these changes to either shut down or to look for simple, comforting stories. One story says that this is all just natural, that climate has always changed and will keep doing so there is nothing special about now. Another says that the situation is hopeless, that the machine is already locked into a track that leads inevitably to catastrophe. The deep time record and the modern data both argue against those extremes. They show that the climate has many possible states, that it responds both to gentle pushes and to shocks, and that the current spike is unusual in speed. They also show that there is room between frozen despair and complacent denial, a space where informed action can still shape outcomes. On a more personal level, understanding the story behind your weather can change how you experience it. The next time a brutal heatwave rolls in, or an out-of-season storm floods a town that rarely sees such events, you will know that you are not just watching random chaos. You are seeing ancient patterns like El Niño, La Niña, and the polar vortex acting on a world that has been warmed by our choices. That knowledge can be unsettling, but it can also be grounding. It tells you that there are real causes, real levers, and real paths forward, even if none of them are easy. You do not have to become a climate scientist to live well in this changing world, but you can choose to stay curious. You can ask how local projects, from new roads to housing developments, account for future flood maps and heat projections. You can support efforts to strengthen early warning systems and protect vulnerable communities. You can pay attention to how energy is generated and used where you live. These are small actions in a vast system, but taken together across millions of lives, they influence the very forces that will shape the next chapters in Earth's climate diary. The climate machine will keep running long after any of us are gone. Ice will wax and wane. Forests will move. Oceans will rise and fall. The question that matters in your lifetime is what kind of world you help leave to those who come after. One where ancient cycles crash into a dangerously tilted stage, or one where their power is softened by a deliberate effort to ease the strain we place on the system. That choice is not written in the ice yet. It is being made day by day in boardrooms and city councils, in fields and factories, in homes, and in the ways we talk about the weather itself. If there is one habit worth carrying out of this story, it is to keep looking up and around with a more informed eye. Notice when seasons drift. Notice when extremes cluster. Listen when forecasts mention distant oceans or polar winds. They are not background noise. They are part of the same living system that feeds you, houses you, and makes your world possible. The coming decades will not be quiet ones for the climate machine, but they can still be years in which paying attention and acting on what we learn makes a profound difference to the kind of planet we all get to call home.